Karthik Velu, make me the host. Okay. Yeah. So it is mu naught divided by 4 pi into 2 times m divided by r cube. Right. So what does this m stand for? Magnetic dipole moment. Right. It is mu naught divided by 4 pi into 2m divided by r cube, where m is the magnetic dipole moment. So this expression has to be remembered for us to understand today's concept. So there is a magnetic field due to a bar magnet along its axial point. Okay. The next topic that we are going to see is solenoid as an equivalent bar magnet. Means we are trying to prove that an electromagnet exhibits the similar property as that of a bar magnet. So that's what this topic is all about. Okay. So see, the derivation is simple, but it is important. Okay. Please make a note of it. Now, see, for us to establish the relation, what we need is, we need to first consider a solenoid. Okay. If you take a solenoid where the windings are very close to each other, you can approximate it to a cylindrical shape. Right? It is as if like, it is like this. So if you look at this diagram, it is as if the wire is wound around it, very close to each other, like this. You're able to see? So they are so close to each other that what will happen is it will approximately look like a cylinder. So when you consider a solenoid of this shape, what we need to do is we need to consider a point on the axis of it. Okay, we have taken a point P on the axis of it, which is at a distance r from it. R from where? R from the center of the axis, or I can say center of the solenoid. Is it clear till this step? Now, if I have to prove that a solenoid is similar to a bar magnet, what is the final result expected at point P? It should be mu naught Are you guys able to hear?
Yes, sir.
Yes, sir.
Okay. So what is the expected value? So mu naught divided by 4 pi into
2m by r cube.
2m divided by r cube. The only difference is going to be when you derived it for a bar magnet, what did the magnetic dipole moment come out as? Just a minute, wait. 1 minute, 1 minute. Just a minute. Okay, mu naught divided by 4 pi into 2m divided by r cube. Okay, so how are we going to derive this? See, we need to consider a small element. Okay, we need to consider a small element. You're able to see this blue color strip, right? Of thickness dx. We need to consider a small element of thickness dx at a distance x from the center of the dipole. I mean center of the solenoid. If I consider it, now this small strip, can I say it is going to act like a circular wire of n turns? So if you take the small strip alone, it is going to act as if it is a small wire, it is a circular wire which has n number of turns present in it. Is it clear till this step?
Yes, sir.
Okay. So when this is happening, listen. Now, due to a circular coil, what is the magnetic field on the axis of it? The other day I told you to revise. See, listen. Due to this circular coil, what is the magnetic field along its axis? What is it? B
Mu
is
naught
equal
I
to
A square.
mu naught I
A square.
n square a
a
dx.
square divided by 2 into
A square plus X square.
a square plus here. What is the value of x? X is the distance from where to where?
Center to the
It is not the distance from the center. See, if you have a circular coil, from the circular coil center, yeah, that's right. From the circular coil center to the point where you're trying to calculate the field, right?
R square minus L square, sir.
It is r minus x the whole square, right? A square plus r minus x the whole power 3 by 2. You guys remember this expression? Right? Mu naught I square divided by 2 into a square plus distance square, the whole power 3 by 2. So this is the value of magnetic field. But what is going to happen here is, since you have considered a small element, the magnetic field will be small, which is dB, and multiplied with the number of turns that are present in that particular portion, the particular blue color step. Is it clear till this step? I have done nothing. I've applied the formula. That's it. Are you guys clear with this?
Yes, sir.
Okay. Now listen. Now, what is the value of capital N? So capital N is equal to what? So what we are going to do is, let small n be the number of turns per unit length of a solenoid. Okay. Then small n will be equal to what? It will be capital N divided by 2L according to the diagram that is given here. Right. So let me say the number of turns here are n dash. Okay. So capital N is equal to n into 2L means small n is equal to capital N divided by 2L means capital N will be equal to small n into 2L. Accepted? Then
yes,
what
yes.
will n dash be equal to? N dash will be equal to the number of turns per unit length multiplied by the thickness of this portion, that is going to be n dash into dx. Sorry, n into dx, right? Is it clear till this step? Now see, I'm going to use the second expression in the first one. Then what will happen is dB will be equal to mu naught I into a square divided by 2 into a square plus r minus x the whole square, the whole power 3 by 2 into small n into dx. Is it clear? So mu naught I a square, in the place of n dash, I'm writing it as small n into dx divided by 2 into a square plus x square, the whole power 3 by 2. Guys, you have to respond whether you're able to understand or not.
Yes,
Or
sir.
else, okay. So what is our work now? Our work is to find the total magnetic field. So for me to find the total magnetic field, what are we supposed to do?
Integrate.
Integrate from where to where? So for calculating the total magnetic field, we need to integrate it from mu naught I a square into n dx divided by 2 into a square plus r minus x the whole square, the whole power 3 by 2. Now tell me the limits. So where is the value of x varying from? The x is varying from where to where? If this is taken as the origin, then this point will be minus L comma 0 and this point will be L comma 0. So what are the limits I need to introduce?
Minus L to plus L.
Minus L to
Yes, minus L to plus L. So if you observe till this step, this dB is equal to whatever it is I wrote, okay, and this one also I wrote. So here, what is the approximation that we are going to do is, R is very much greater than A, means the distance from the center to whichever point you are trying to calculate the field, it is going to be very much greater than the radius, and R is also going to be greater than or equal to L, because we are trying to bring a similarity to a bar magnet, which is very small. You remember in the previous class I told you bar magnets, magnetic field I'm finding at the axial point, which is small in nature. In a similar way, here also if it has to be small, then R should be greater than or equal to A and R should be greater than or equal to L. Okay. If that is the case, when R is very much greater than A and R is very much greater than L also, then what will happen is A square plus R minus X the whole square, the whole power 3 by 2 is approximated to R square the whole power 3 by 2, which is equal to R cube. So if I call this expression as 3 and this expression as 4, then I will use 4 in 3. Then what will be the value of B? B will be equal to integral of minus L to L mu naught I n a square into dx divided by what will happen to the denominator? That whole thing
R
can be
cube.
written as
R
R
cube.
cube. Now tell me, what are all the constants that are present in the expression and what is the variable?
mu naught n
mu
is
naught I n a squared by 2 R
R
cube.
cube. Is it a constant or a variable?
constant.
Constant.
So this whole thing is a constant because none of them are dependent on whom? None of them are dependent on x. Right? So all these things are constant. So if they are constants, what can be done to them? They can be taken out of the integral. When you take out of the integral, mu naught I n a square divided by 2 r cube into integral of minus L to L dx. What is the integral of dx?
X.
X.
A square divided by 2r cube into integral of x dx is x from minus L to L. If you integrate it, what do you get? Mu naught I
2L.
a square, yes, 2r cube into 2L. This n into 2L is what? We have already written that expression. The small n,
Capital N.
it is capital N. So this will be equal to mu naught ni a square divided by 2r cube. This is going to be the final expression for B. Is there any doubt till this point? Is there any doubt till this step?
No, sir.
All right.
Oh, sir.
So listen. So what is the expression we need? We will again write it. It is mu naught divided by 4 pi is needed into 2m divided by r cube is needed. Okay. Now, what is a magnetic dipole moment due to a current carrying conductor? It is I into
A.
A. So, if you observe mu naught divided by 2 r cube, I am not disturbing. This n into I into this a square is there. No? So, I will multiply it with pi and divide it with pi. Okay. And I will multiply the numerator with 2 and denominator with 2. When I do this, then I'll get mu naught divided by 2 into 2 is 4 pi r cube into 2 times, what is this, ni into pi a square?
M.
M.
Magnetic dipole.
Did we get that expression? So mu naught into 2m divided by 4 pi r cube is the required expression. So this is the expression generated due to a solenoid. And this is the expression we generated yesterday due to a bar magnet. Now can we say that they both are similar? Provided certain measurements are taken into consideration. There the bar magnet has to be small. Here the solenoid has to be thin. Its thickness should be very small and it should be long. Okay, make a note of it. I'll give you 2 minutes time. I want you to write this. So from where should I show? From here or should I go to the next page?
From here.
I suggest you guys to write it, okay? Don't take screenshots and all, write it. Because this derivation seems to be simple. See, it's actually simple only, but you need practice.
Sir, if we
Yes.
take the area element, the circular coil element, if we take it
Yes.
accordingly, so that we integrate it between 0 to 2L, Naka, is it fine?
Like
You'll
how?
get the same explanation. This thing, it's
This, here itself, you want to multiply with pi and divide it with pi.
no, sir. On the you see that dx that circular coil, no, sir. If you take it at
This
one
one.
end,
You should take it. You want to take it. If you take it at one end, it can be 0 to 2L. That is also right.
if we do that, if I don't remember this and I write that in the exam, is it fine?
It is fine according to me, but see, this is the one. The reason I taught you this is because it's there in NCERT. I have exactly taken whatever is there in NCERT and I've taught.
Okay,
So
sir.
90% remember it. Okay, it's not a big deal. I'll tell you what. See, I can teach you the technique, but I cannot say whether you will get marks for that or will strike it off. It again depends on the examiner only. Okay, I'll tell you how you can remember. So most of you might get scared looking at these integration. So wherever you need to integrate in physics, okay. So wherever you follow this integration, I'm talking about throughout physics, not only for this derivation. You take one particular point as origin. These are the common steps you will follow. One fixed point as origin. Okay, this is very important. Second, from the fixed point, at a distance x, consider an element of thickness dx. Okay, you're able to understand?
Yes, sir. Yes, sir.
So third is, you need to frame a mathematical expression. Try to write the required expression for whom? For a particular physical quantity. In this case, the physical quantity is magnetic field. For a physical quantity, in terms of whom? In terms of dx and x. Then the last one is integrate with proper limits. You take any particular derivation based on integration, you will follow the same steps, nothing outside this.
Yes.
So if you have a clarity of this, that is more than sufficient. So only thing you need to remember is this origin. If you, so I got what you're asking. If at all you don't remember that you have to take center as origin, then can I take 0 to 12? It is absolutely right. It is absolutely right. You will get the same answer.
Yes,
No doubt about it. But the only thing is, I'm not sure to what extent they will accept it.
Oh, okay, sir.
Okay, because see, your teacher might say, so some other school teacher might say it's fine. So I cannot give assurance on that, because this is the derivation that is given in NCERT. Mostly the answer key is prepared only according to NCERT. Okay, so I suggest you go with this. Want to make a note of it? Till where have you written?
Sir, please wait, sir.
Yeah, I'll wait. Should I display this page?
No, sir, this is fine.
Yeah.
Sir, can you scroll option?
1 minute here.
Yes, sir.
So let me know once you're done. Done?
Yes, sir.
Yes, sir.
1 minute, sir.
Sorry? You want me to wait?
Yes, sir.
Okay, right. So I'm moving on to the next concept. So next part is torque acting on a magnetic dipole. Okay. So torque acting on a magnetic dipole. You guys remember what is a torque acting on an electric dipole? Torque is equal to
QDIA.
P vector cross E vector. So torque is equal to P vector cross E vector, where P vector is what? Dipole moment,
Dipole moment.
and this is the electric field. So it is the cross product between the dipole moment and the electric field. In a similar way, what do you think will be the expression that will be deriving here?
Magnetic dipole moment cross
Magnetic dipole is
M vector
magnetic.
cross B vector.
MB cos
vector cross
theta.
B.
It will be M vector cross B vector. As simple as that. Okay. So how to derive that? Tell me. Okay. So you have a north pole and a south pole. So between a north pole and a south pole, you have placed a magnetic dipole. So there is a magnetic dipole which also has a north pole and a south pole associated with it. So the north pole of this magnetic dipole will experience a force in this direction of how much value? So remember last class I told you B is equal to F divided by M. Instead of M, I will write it as Q so that you are not confused. So what does this QM stand for?
Pole strength.
Pole strength. So F will be equal to QM into B. So that's what is given. Instead of QM, they have given it as MB. Similarly, the south pole will get attracted towards the north pole and its value is also QM into B. Okay. So if you take this as the center, if this total length is 2L, then how much will this length be? It is going to be L and this length is going to be L. Then what will this distance be, guys? What will this perpendicular distance be? I'm zooming and showing.
L sin theta.
It will be L sin theta. And this perpendicular distance is also L sin theta. So what is the formula for torque? Torque is equal to R vector cross F vector, the basic formula for torque, or you can define it as force into perpendicular distance. So what is the force acting on the particle? Qm into B into what is the perpendicular distance?
L sin theta.
It is L sin theta. Similarly, torque experienced by the south pole, it is going to be Qm into B into L sin theta. Now use right hand thumb rule and you guys tell me in which direction will the torque act? In which direction will the torque act?
Minus K cap.
That's right. It is minus K. There is also minus K because in which direction is the dipole going to rotate? Clockwise or anti-clockwise?
Clockwise. Anti-clockwise.
No, it will rotate in this way. It's clockwise. So clockwise moments are negative. That is why it is minus K cap. So what will be the net torque acting on the particle? Net torque will be Qm into B into 2L sin theta. But what is pole strength multiplied with 2L? Last class, it is magnetic dipole moment.
Magnetic.
So this will be MB sin theta, or torque vector will be equal to M vector cross B vector. So here I wrote magnitude, here I wrote in the form of vector. So torque vector is equal to M vector cross B vector. See, to my knowledge, they will not ask you the derivation for this. Okay, because the derivation is similar to what we have already seen in electric field, that is more important. But here I showed you because you need to understand how to use the concept of pole strength. So I suggest you to make a note of it so that you get clarity. Done? Similarly,
1 minute.
yeah, make a note of it.
Done, sir.
Okay. So the next one is potential energy of a magnetic dipole in uniform magnetic field. So potential energy of in uniform magnetic field. Okay. So what is it you have? You have uniform magnetic field present, right? You have a uniform magnetic field present in which what is placed? A magnetic dipole is placed. Now our work is to find what is the potential energy of this. How do we find? If this is the north pole, this is the south pole. Since the magnetic field is from left to right, left side will act like which pole and right side will act like which pole?
Left side as North Pole and right side as South Pole.
Yes. So this is north pole and this is south pole. And this is going to be the axis of the dipole. Okay. Let's say the axis of the dipole is making an angle theta with the direction of the magnetic field. So what was the potential energy due to an electric dipole? Potential energy due to an electric dipole was what?
Minus KQ
Minus,
Q naught by R.
no, that is between system of charges.
Minus PE cos theta.
Minus P vector dot E vector or minus PE cos theta. You remember there was a concept of stable equilibrium and unstable equilibrium. There what we discussed. So what do you think will be the answer for this one? UB will be equal to what? Minus P vector is supposed to be replaced with M vector dot B vector, or it is going to be minus MB cos theta. Okay, how to derive this? So for you to calculate the potential energy, wherever you need to calculate energy throughout physics, you need to calculate the work done. Right? dW is equal to torque into d theta. Let's say the dipole is rotated through a small angle d theta, then dW is equal to torque into d theta. Then dW will be equal to, what is the value of torque that we derived?
MB
It is
sin
MB
MB
sin
sin theta into d theta. So integrate it from theta 1 to theta 2. Then the total work done will be equal to MB into integral of sin theta is minus cos theta from theta 1 to theta 2. So it will be minus MB into cos theta 2 minus cos theta 1. Okay, minus MB into cos theta 2 minus cos theta 1. Or this can also be written as minus M vector dot D. So this work done is what is going to get stored in the form of potential energy. I hope you remember all these things. Minus M vector dot D1.
So can you show the diagram also?
Sure.
Thank you, sir.
Yeah. So are you done? Is everyone done with it? Minus M vector dot B vector. Okay, we'll be seeing everything similar to what we saw in the first chapter.
Sir,
Shall I
what is theta 2 and theta 1?
Theta 2 is some angle, that's it. Initial some theta 1, it started at some theta 1 and it went to some theta 2, that's it.
Okay.
Maybe if I take it like this, after some time, maybe the dipole is making an angle theta 2, something like this. So I'm changing from initial to final. Shall we move on?
Yes, sir.
Now listen. So, I told you, right, this chapter has 3 parts. The first part is about, you'll be learning about a bar magnet and these kind of concepts. What will happen when you place a dipole in uniform magnetic field. That is the torque, potential energy, and all those parameters. And the last one is Gauss law in magnetism. So, this will be the last topic of the first subpart. Okay. So, it is a very simple expression. So, for Gauss law, what is needed? Gauss law mainly speaks about what?
Magnetic flux. I mean, electric flux.
No, Gauss law need not speak only about electric flux. Gauss law speaks about flux. If it is Gauss law for electrostatics, it speaks about electric flux. If it is for magnetism, it speaks about magnetic flux. Okay. So here the heading is Gauss law for magnetism. So concentrate. So how you define the flux? Surface integral of whatever field you have in your hand dot dA vector. Some books write it as ds vector because you're talking about the surface area. Okay, I think here it is given as ds. Yes. But it doesn't make any difference. So integral of the surface integral of b vector dot dA vector. So in the case of electrostatics, what was it? E vector dot dA vector is equal to q in divided by epsilon naught. Means 1 by epsilon naught times the charge enclosed by whom? What does it? By the Gaussian surface, right? So for us to apply the Gauss law, we need to consider a Gaussian surface. So remember one important property about electric field. Electric field will never form closed loops. Do you guys remember this? So when I give you a positive charge and a negative charge, if I ask you to draw the electric field lines, you say the electric field lines start from the positive charge and they end with the negative charge. There is no concept like it forms a complete loop. This is wrong. Whereas in the case of magnetic field, what will happen?
They form closed loops.
So they form a closed loop. Means if it is going like this, then there is a concept of coming back also. Right? So here if I consider a Gaussian surface, what will happen? So if I consider a Gaussian surface, in the case of electric field, I will speak only about the concept of the electric field lines leaving the Gaussian surface or electric field lines entering the Gaussian surface. This is what we speak.
Yes, sir.
Whereas in the case of magnetism, what will happen is, since the number of electric field lines that are going out will be equal to the number of electric field lines that are coming in, only because of what reason? Only because the magnetic field the magnetic field forms a complete loop. So since it forms a closed loop, what will happen is there will be no field line that is enclosed within the Gaussian surface. It will be equal to 0. This is what is Gauss law for magnetism. It is a very simple expression. There is no problem to be asked on this because it is always a 0. Whereas in the case of electric flux, it was important, right? Gauss law had so many applications. But in the case of Gauss law for magnetism, there is no application as such. It is always a fixed value which is equal to 0. And what is the reason for it? The net magnetic flux through any surface is always 0 only because the magnetic field lines form a closed loop. Okay, make a note of it. Maximum they can ask you is for 1 mark, that's it. Nothing outside that. So with this, the first part of the chapter is over. Is there any doubt till whatever we discussed? Now you guys can go and refer the deleted portions and all those things. You can have a look at it. I've explained everything. Whichever is needed, I've explained so that you will understand better. Okay. So the deleted portion will not be considered for. That is the only thing that is going to happen. Okay. Now you guys decide on it. Shall I move on to the next concept? Right? Yes or no?
Yes, sir.
Shall I
Yes,
move?
sir.
Okay. So as I told you, the first part is over. The second part is, see, generally in your textbook, it is given, the Earth's magnetism is given, but that's a very light concept. We can deal it at the end. Now I want to concentrate on magnets and its properties. Okay. See, the tricky part about this portion is all the words will be similar. So I want you to concentrate well. All the words will be similar. Okay. But they have a slightly different meaning. If you understand this, you will have a clarity about other things also. For example, if you have written the test which I gave you, there was a question like this, right? If you have an inductor, in the inductor, if you insert an iron rod, will the bulb glow with greater intensity or lesser intensity? Intensity in the sense brightness. So was there a question like this when I gave you for alternating currents?
Yes, sir.
Yes,
So
sir.
the answer to that lies in this chapter. Okay. Means you need to know the concept of permeability, especially this part of the chapter, which is very important. Okay. So concentrate. Similarly, when we discussed about transformer also, I would have told you one point. We use a soft iron core. So we use a soft iron core. Why we use only
To
soft iron?
reduce eddy
Yes.
currents.
Eddy currents.
To
It
reduce
has
eddy.
high
current.
That is the
Hysteresis.
it has high permeability.
yeah. So we discussed about this. You know, not only reducing about eddy currents, it has some concept like how much magnetism it can retain. There is a concept like retentivity, something like that. Okay, that the answer for that also is given in this part. Similarly, in the same transformer, we discussed about hysteresis. Right? I told you I could not explain. I cannot explain at that time. So the answer to that also will be given in this particular portion. So concentrate. So here it is mostly definitions only, but those definitions are very important for you to understand. If there is any doubt, please ask. So I'm moving on. Write down the heading as magnetic properties of a material. Magnetic properties of a material. So if you can ask me what there also in the previous topic also we discussed about magnetic property only, but there what was the material we were concentrating on? We concentrated only on the bar magnet. Whereas here we are going to discuss about all the materials. I told you one important point here. Remember, every material is made up of atoms, and atoms are made up of electrons. Every electron is going to revolve in an orbit. So every material is going to have magnetism associated. But the extent to which it is going to have, the answer to that is again known in this part. Shall I start? So there are a few definitions. The first part is called as magnetic permeability. Okay. So make a note of it. Magnetic permeability. So how do you define it? 1 minute. So what is magnetic permeability? So it is the ability of a particular material. The name itself is suggesting, right? Permeability, the extent to which it will be able to get magnetized. Okay. It is the ability of a material to permit the passage of magnetic field. Yeah, tell me.
Sir, someone is chatting with me personally, sir. It is also named as Darshini Umapati, sir.
Really? I'll have a look at it. One minute. Anyways, I can find it out after the class. Don't worry. Okay, now you will not get messages.
Yes, sir.
Yeah. So what were we discussing? Magnetic permeability, right? So it is the ability of a particular material to get magnetized. Means the extent to which it will allow the magnetic field lines of force to pass through it. And its expression, we already know, right? Mu naught, we have seen. Mu naught divided by 4 pi, I told you already. Mu naught by 4 pi is how much? 10 power minus 7. So mu naught is equal to 4 pi into 10 power minus 7. We already know this, right? So what does this mu naught stand for? It is the permeability of free space or vacuum, right? But whereas when I'm talking about only mu, okay, don't get confused between this mu naught and mu. In physics, wherever you use a circle as a suffix, that is mainly used for vacuum or air. Okay. Here magnetic permeability mu is given as B divided by H, where B is called as the magnetic induction and H is called as the magnetizing force or magnetic intensity. Please make a note of it. Write down the formula. So mu is equal to B divided by H, where B is called as what? The magnetic induction. Okay. And H is what? H is defined as the magnetizing force or magnetic intensity. I will explain everything. Shall I move on to the next one? Is it clear?
Yes, sir.
Yes, sir.
So the first term is about magnetic permeability. See, if there is any confusion, please stop me. I don't mind explaining again. Don't be with confusion. Okay. So next is magnetizing force or magnetic intensity. This is the second definition. So which is represented by the symbol capital H. So we have seen it here. Seen here, no, magnetic intensity. The other name for magnetic intensity is magnetizing force. So what do you think is magnetic intensity? By looking at the name, what do you think it will do?
Sir,
See,
how much it can magnetize another object?
how much it can magnetize another material. See, I'll give you a simple example. Okay? Not sure if you people have magnets at home. If at all you have, you can do the small activity and see. See, you have a small magnet in your hand. Let's say you have a small bar magnet. Let's say you have scissors, or you have a knife, something, or you can take a door handle also. You take this magnet and rub it against the scissors for some time. Have you ever observed that the scissors will start attracting other particles?
Yes, sir.
You would have observed it, right? So it does it. So initially, before you rub this magnet against the scissors, what do you
Sir,
think? Will the scissors be able to attract? Yeah.
sir, again it's replying something, sir. It's saying like I'm a hacker, I'm a hacker.
I'm a hacker.
Hacker, sir.
Okay.
I mean, the maximum it can do is personal message, there should be anything.
Yeah, that should. Anyways, I can find it out from the IDs. You people are logging in, right? Let's see whose ID it was.
Sir, or you can disable chat fully, sir. Not even between Epsilon Academy and us.
I'll do, but I'm not able to disable completely.
Sure.
No one.
No one,
Okay.
sir. No one.
No one, sir.
Okay, let's see. Let's see this. Anyways, I can find it out from the mail IDs once I get the report. Don't worry about it. Even if you get, ignore it. Okay, don't worry about it. If you get some message, also ignore it. Nothing serious. I'll find it out. Okay. So, what were we discussing? Yes. So, before you try to rub this magnet against this iron particles or something, a material, will that scissors have the property to attract some other material?
No, sir.
The answer is no. Right. So, where did it get the property from? So, it got the property from the bar magnet. Because bar magnet is a permanent magnet, some of its property, attractive property, is transferred to the scissors so that it is able to exhibit. So, let's say I have a small bar magnet, I rub it for 2 minutes. Or let's say 15 seconds, I rub it, the scissors is able to attract. If suppose I take a bigger bar magnet of a greater intensity, I rub it against the same surface with the same intensity for 15 seconds. Now, which one will have the tendency? So, in which case do you think the scissors will have better attractive property?
With the bigger magnet.
Big magnet. With a bigger magnet.
When you obviously rub it with a bigger magnet, right? So, from this, can I say that the bigger magnet is going to have a greater magnetizing force compared to the smaller one?
Yes, sir.
Yes,
Yes,
sir.
sir.
So this magnetizing force is nothing but the extent to which an external agent, here who is the external agent? The magnet. This is scissors is the system under us. So the extent to which the external agent is able to magnetize a given material is what is called as magnetizing field intensity. Are you guys able to understand? So that's what we call it as magnetizing force or magnetic intensity. And it is given by the expression H is equal to B divided by mu. It is nothing but the rearrangement of the above expression. Mu is equal to B divided by H. H is equal to B by mu.
Sir, I have a small doubt, sir.
Yeah, tell me.
How does the magnetism, the property of magnetism, how does it get transferred in the first place, sir?
It is not about transferred in the sense some particles of the magnet might get attracted due to friction.
Yes, sir.
So that's what happens. Okay. So
So it's
all
not
like,
the actual scissor showing the magnetism, but the
no,
particles of the magnet.
it is actually not the scissor. The scissor has got magnetized.
Okay, sir.
Okay.
Okay, sir. I understand.
So here there is a confusing factor that gets arised. Okay. He's asking a valid question. See, there are two things. One is magnetizing. The second is magnetized. Okay. These are the two words you need to have a clarity of. Magnetizing. So you can either use S or Z, and it doesn't make sense. It doesn't make a difference. Magnetized. So these are the two words. So magnetizing is a property of whom? Who can magnetize?
Bar magnet.
Bar magnet.
Externally,
The magnet.
the external magnetic field. Am I right? So it is the external magnetic field. Like it may not be bar magnet. In this case, it was bar magnet. It can be some other magnet also. So let's try to extend our knowledge, saying that magnetizing is done by an external magnetic field. As simple as that. Then who's getting magnetized? The material which is subjected to the external magnetic field is the one which is getting magnetized.
In this case, the scissors.
The scissors is the one which is getting magnetized. The one which is receiving the magnetic field will get magnetized. The one which is giving the magnetic field will have the tendency to magnetize. Okay. So here, this intensity of magnetization, don't get confused between magnetic intensity and intensity of magnetization. They both are different again. Magnetic intensity is the degree to which a magnetic field can magnetize a material. It is given as B by mu. Shall I move on to the next one so that you will understand what is the difference?
Yes, sir.
Okay. Next is intensity of magnetization. I told you, right? They both will be same. Intensity of magnetization means the magnetic dipole moment that is created, means the output. I'll explain what it is. See, suppose I have a small iron bar in my hand. Okay. Now what will happen is, if I have North Pole and South Pole, I'm placing an external magnet, or I'm subjecting it to external magnetic field. I'm placing this in an external magnetic field. Then what will happen? What will happen inside? Do you guys remember the concept of dielectric and polarization? So we discussed something like dielectric and polarization. What will get induced inside the dielectric? So when you place a dielectric in external magnetic field, what will happen?
Internal magnetic field.
So there will be a magnetic field there will be an electric field which will get induced inside due to the concept of polarization, right? In a similar way, what will happen is every material will have small magnetic dipoles within it. This is accepted because every material has a magnetic dipole moment due to whom? Due to the revolution of electron. So when this is going to have small magnetic dipole moment, what will happen is, see, let's apply the logic. Let's say I'm taking one of such dipoles. Let's say it is like north and south. Is it clear till this point? So this is the iron rod which I have in my hand, and I place that iron rod in the external magnetic field. Now I'm trying to analyze what exactly is happening to it inside. Okay. So inside an iron rod, by default, there is a small magnetic dipole which is present. Small magnetic dipoles are present like this. Now, according to the previous concept, when you place a small dipole in external magnetic field, what will happen? We saw that already. It experiences, yes, it experiences torque. So, due to torque, what will happen is it will start rotating and it will try to attain a stable equilibrium. Right? So, when it is going to attain a stable equilibrium, see, since this is the north pole outside and this is the south pole inside, can I say that this dipole will get rotated and it will be like this, accepted? Because the south pole of the internal dipole should be close to the external north pole. Yes or no? That is the way in which it is supposed to rotate. It will rotate, according to my previous diagram, it should rotate anti-clockwise and stop at a particular position. So when this is going to happen, can I say that there is an aligned magnetic, so there will be one more dipole also which is like this. Sorry. There will be one more dipole also like this. South, north, it will be like this. So what is the direction of basic dipole moment? So dipole moment is always
South to north.
South to north. Whenever you get a doubt, refer it to electric field. The same thing is applicable here, south to north. So this is the direction of dipole moment. So this dipole will have a dipole moment. This dipole will have a dipole moment. So everything is there. So each dipole moment, let me call it as mu1, mu2, and these are all vector quantities, correct? So due to the small dipole moments generated by all these dipoles, there will be a net dipole moment that is existing. Accepted? Did you guys understand what exactly is happening inside? So inside the iron rod, there were some dipoles which were randomly aligned. But due to the presence of external electric field, it experienced torque and it attained stable equilibrium. Due to the stable equilibrium, what is happening? The magnetic dipole moments are aligned in a particular direction, due to which there will be a net dipole moment. So now look at the definition of intensity of magnetization. The magnetic dipole moment developed per unit volume. This magnetic dipole moment is what they are trying to talk about. The magnetic dipole moment developed per unit volume is what is called as intensity of magnetization. Means the extent to which the material has got magnetized. Is it clear? Meaning, if I take this particular portion and I say this portion's volume is 1 unit. Okay. And in this 1 unit of volume, there will be some dipole moment. That dipole moment developed per unit intensity of magnetization. Are you guys clear? Is there any confusion you people are having between magnetic intensity and intensity of magnetization?
Sir,
Yeah, tell me.
sir, will the dipole moment that is present on the top and bottom not repel each other?
No, it will not. Because the dipole moment is along horizontal only, no?
So there will be no repulsion.
No, there will be no repulsion because they will be very close to each other. See, generally the technical name given to it is a domain. That's not there in your syllabus, so I'm not trying to explain it. We call them as domains. Okay, so that nothing of that sort will happen because it has already attained stable equilibrium. So who will control it? Due to whom has it got this stable equilibrium? Due to the external field, so that we take care of. Okay, so make a note of it. So tell me only one thing, guys. Is there anyone having a confusion between magnetic intensity and intensity of magnetization? Magnetic intensity is defined for external field, whereas intensity of magnetization is defined for whom? Defined for the field produced within the magnetic material or within the material. Okay. Okay. So the intensity of magnetization is represented with I. So some books actually they use capital M again. So you need to be very careful while noting it down. Shall I proceed to the next concept?
Yes, sir.
Yes. Okay. And the next term is called as magnetic susceptibility. So this symbol is like this. It is not X, it is chi. I guess you would have learned in electrochemistry something. Right? So magnetic susceptibility, we call it as chi M. See, the word susceptibility looks to be so tough, but the actual meaning of susceptibility, if you look at the dictionaries, it is vulnerable. Okay. So magnetic susceptibility means the extent to which a material can get easily magnetized. And I'm talking about basic thing. I'm not talking about the technical definition. So magnetic vulnerability means, generally, if you don't know the meaning, vulnerable means how easily something can get affected. Okay. So susceptibility is a synonym of it. Okay. So magnetic susceptibility is like this. So technically it is defined like this. The ratio of intensity of magnetization, that is like output, applied. So who is the input? It is the magnetizing force. So the ratio of intensity of magnetization to the magnetizing force is what is called as magnetic susceptibility. It is something similar to efficiency of a material. Are you guys able to understand?
Sir, can you explain it again, sir?
Yeah, sure, I'll do that. See, magnetic susceptibility means, so magnetic intensity, what is it? Magnetic intensity is represented with H. It is B divided by mu. Intensity of magnetization, what is it? It is mu divided by capital V, right? So intensity of magnetization is mu divided by capital V. Now, the susceptibility is defined like this. It is defined as the ratio of intensity of magnetization divided by the magnetic intensity. So this is the input. This is the output that is getting generated. So it is like output divided by input. So generally, what is output divided by input? It's called as efficiency. Right. So susceptibility it's something similar to efficiency. I'm just using the word efficiency for you to remember. That's it. Don't write the word efficiency and tell, okay, don't do that mistake. You have to go with this
Thank
definition.
you, sir.
Yeah. Clear?
Yes, sir.
So these are all the definitions that are related to the magnetic properties of a material. It's not at over, wait. So based on all those things, what we will do is we will do a comparative study between diamagnetic material, paramagnetic and ferromagnetic material. For example, if you see what is susceptibility, what is the relative permeability, then we will see variation of M with H. We will see all those things, okay? So this will give you the answer for hysteresis effect also, what it means. Okay. See, since these definitions are slightly tough, I'm giving you some more time to prepare this. So we will discuss about this table in the next class, and next class we can maximum complete this chapter also.
Sir?
Yeah.
So in intensity of magnetization,
Mm-hmm.
the formula is given I is equal to magnetic dipole by volume, no sir?
Yes.
How is it then simplified by pole strength by area?
Because see, magnetic dipole moment, what is the formula? M into 2L divided by volume is nothing but area of cross section into its length. So 2L and 2L will get cancelled, M divided by.
Okay, sir. Thank you.
Okay. Okay. See, I've not yet explained the mathematical details. I'm not going in depth of why this B is equal to mu naught into H plus I. This and all are coming. This I'll explain in the next class. No hurry. Okay. You first get clarity of these definitions, and then we'll see it in the next class. Okay. So, is there any other doubt you have from today's class?
No, sir.
Can you send it this page, sir?
This page, yeah, I'll do that.
Yeah.
I'll send
Thank
you
you,
a
sir.
different. I'll send you a different set of definitions also because sorry. Anyways, I'll share it with you. Just a minute, guys.
So will you be sharing the notes also?
I'll send for that particular page. Okay.
Okay, sir.
Wait a minute. Don't leave.